Have you ever stopped to think about what actually makes your phone work? Or your TV? Or even a simple traffic light? It's not magic, right? It's this hidden world of tiny, tiny components. And guess what? They all speak the same secret language. So today, we're going to decode that language. We'll pull back the curtain on the essential building blocks that literally power our world. Ready? Let's jump in.
Okay, here's the game plan. First up, we're going to learn the language of circuits. Then we'll build up our basic toolkit, all the essential bits and pieces. After that, we'll look at how you actually measure electricity. And to wrap it all up, we'll get into the really cool stuff, resistors, these clever little components that let our gadgets react to the world.
All right, first things first. Before we can even think about building something, we have to learn the lingo. It's kind of like learning to read music. Instead of notes, electronics has its own set of universal symbols, and once you get these down, you can read pretty much any circuit diagram anywhere in the world. It's pretty cool.
So you might be asking, why even bother with symbols? Why is this language so important? Well, just imagine for a second trying to draw a realistic picture of every single wire, every tiny chip inside your laptop. The blueprint would be an absolute nightmare, right? A total mess. So how in the world do engineers design this super complex stuff without getting totally lost?
Well, the answer is actually pretty simple and kind of beautiful. They use a universal language of symbols. Every single component, from a big battery down to a tiny little LED, gets its own special icon. And what that means is an engineer in Tokyo can look at a diagram from an engineer in Toronto and know exactly what's going on. It's a global language for building the future.
Okay, so we've got the language down. Now, let's open up the toolbox. We're going to look at the absolute fundamental components. Honestly, you can think of them like the essential Lego bricks you need to build pretty much any electronic gadget you can dream up. First up, the power source. Every single circuit needs a heartbeat, right? A source of energy. And that's the job of the cell, or, a battery. It's the engine. It provides that electrical push that makes everything else actually do something. Okay, power is great, but we need control. That's where the switch comes in. Its job is super simple, but absolutely critical. It's basically the gatekeeper for electricity. You close the gate, you complete the circuit, and everything's on. You open it, you create a gap, and the flow stops dead. It's our on and off button.
So, we've got power, we've got control, but how do we know anything is even happening? The easiest way is with a good old-fashioned filament lamp. When that electric current flows through it, the bulb glows. It's that instant, satisfying feedback that tells you, hey, my circuit is working. Every system needs a failsafe, a safety valve, and in electronics, that's the fuse. I like to think of it as the circuit's bodyguard. If there's a sudden, dangerous power surge, the fuse literally sacrifices itself. It blows, breaks the connection, and saves all the other more expensive components from getting totally fried.
Next up, meet the circuit's traffic cop, the diode. This little guy enforces a very strict one-way street for electricity. The current can flow forward, no problem, but try to go in reverse? Nope, it's completely blocked. And this simple rule is so important for protecting sensitive electronics and just making sure the power is going exactly where you want it to.
Now, what if you take that one-way street idea and you add a cool bonus feature? Well, you get one of the most common components in the world today, the LED, or light-emitting diode. It does the exact same job as a regular diode, controlling the flow, but it also lights up when it's working. And they're super efficient, which is why they've pretty much replaced old light bulbs in everything from traffic lights to, probably the screen you're watching this on right now.
Okay, so we've got our basic toolkit together, but how do we know what's really going on inside those wires? Electricity is invisible, right? To actually see what's happening, we need a couple of special tools. The two main tools of the trade are the ammeter and the voltmeter. They sound similar, but they do very different things. The ammeter measures current. That's the actual amount of electricity flowing. To do that, you have to place it in series, basically sticking it right into the path of the current, like a water meter in a pipe. But the voltmeter, that measures potential difference, which is more like the electrical pressure. So you connect it in parallel on either side of a component to see the difference between the before and after. So building and measuring is cool and all, but what if we need to control the flow? Like, what if we need to slow it down a bit, fine-tune it? For that, you need a component that's specifically designed to, resist the flow. So welcome to the world of resistors.
Now, resistors aren't all the same. They come in a few key types. You've got your basic fixed resistor and your variable resistor, which let you set or adjust the resistance. But then you get the really smart ones, the light-dependent resistor, or LDR, and the thermistor. These guys can actually react to the world around them. Let's check them out.
First, the simplest one, the fixed resistor. And the name pretty much says it all, right? It provides one specific, unchanging amount of resistance. That's measured in ohms, by the way. You pick the value you need for your circuit, and it just does that one job, reliably, every single time.
Now, the variable resistor takes things up a notch. This component lets you actually change the amount of resistance. It gives you direct, hands-on control over the current. If you've ever used a dimmer switch for a light or turned the volume knob on a stereo, you've used a variable resistor. That's exactly what's going on inside.
Okay, this is where it gets really cool. This is where our circuits start to get smart. We're moving past just turning knobs and flipping switches. Now we're going to look at components that can actually sense the world around them and react all by themselves. So say hello to the light-dependent resistor, or LDR for short. Think of this thing as a tiny electronic eye. When you shine a bright light on it, its internal resistance just plummets, dropping to almost nothing. It basically opens the floodgates and lets all the electrical current rush through. But the second you put it in the dark, the complete opposite happens. Its resistance skyrockets. It becomes huge. It builds this massive wall that blocks pretty much all the current. And this simple on-off switch that's activated by light, it's the secret behind tons and tons of automated gadgets.
So, what's a real-world example? A burglar alarm. It's perfect. Imagine an LDR sitting in a dark room. Its resistance is super high, so the alarm circuit is off. But then, an intruder shines a flashlight. Bam! The light hits the LDR, its resistance instantly drops to zero. Current suddenly flows, and the alarm starts blaring. It's such a simple but brilliant way to use a sensor.
All right, our last component for today is another one of these smart sensors. But instead of seeing light, this one feels heat. It's called a thermistor, and it works in a similar way. When things get hot, its resistance goes down, letting more current flow.
And you guessed it, when it gets cold, the thermistor's resistance goes way up, blocking the current. This behavior makes them absolutely perfect for being temperature sensors. You'll find them in car engines to monitor temps or inside that electronic thermostat on your wall that controls your heating.
So, there you have it. In just a few minutes, we've gone from simple symbols on a page all the way to smart components that can see light and feel heat. These are the absolute fundamental Lego bricks of all modern technology. So now that you know the toolkit, I've got a question for you. What would you build? What kind of problem could you solve with just a simple switch, a light, and a sensor? The next huge idea could start with a circuit just like the ones we've talked about today.